So we have an initial state of 1 mole of ideal gas at constant some pressure and at a temperature. And we want to determine the change in entropy for this gas undergoing a reversible isothermal change in pressure, a reversible adiabatic change in pressure, and a constant volume change in pressure. Again, using our expression for the molar, excuse me, the molar heat capacities. Okay, this P1 equals 10 atm, T1 equals 300 K, N1 equals 1 mole, and V1 now is equal to N RT divided by P is equal to 1 times 8.2 times 10 to the minus 2 times 300 divided by 10 is equal to 2.46. Okay. For an isothermal change in pressure, we have the new pressure is 5 atm. It's isothermal, so the temperature stays the same. Moles stay the same. And the volume now is still given by gas law. So it's going to be nRT over P is equal to 1 times 8.2 times 10 to the minus 2 times 300 divided by 5. V2 is equal to 4.93 liters. And because we're calculating the entropy, we're going to just try to get the change in the heat. Delta T equals 0. Therefore, delta U is equal to 0 because it's an ideal gas. And that means U equals W is equal to N RT natural log V2 over V1. Right, we solved this in chapter 2 over and over and over again for an ideal gas. And this is going to be equal to 1 times 8.314 times 300 times natural log of 4.93 divided by 2.46. Oh, sorry, 2, which means that Q is equal to when I did the calculator work, I didn't write that out. But what I do have is that delta S gas is equal to Q over T is equal to N R ln V2 over V1. So taking all of this, substituting into there, we get delta S gas is equal to 5.763. That's joule per Kelvin. This is page 11. So that's the first part of the problem. The second is, what if instead we have a adiabatic, and it's reversible, adiabatic, which means Q equals 0. Well, that implies delta S is equal to Q over T, delta S equals 0. So that wasn't so bad. And the final question is about a constant volume decrease in pressure. And we're going to have to do a little bit more work here. And you'll see if you write things out why that is. So we have du is equal to T ds minus P dV, which means ds is equal to du plus P dV over T. And we also have that du is equal to N CV dt, P is equal to N RT over V, which we can then substitute into this to get ds is equal to N CV over T dt plus nRT over V T dV. So these T's cancel out. And this gives us an expression for the change in entropy in terms of these variables. In this particular problem, this is a constant volume, which means this goes to 0, and we're left with this. So integrating that, we get delta S is equal to N CV natural log T2 over T1. And this is a constant volume process, so we're saying that this is saying that P1 T1 is equal to 300, Kn1 is equal to 1 mole, V1 is equal to 2.46 liter, constant volume, so V2 is equal to 2.46 liter, N2 is still equal to 1 mole, P2 is now equal to 5 ATM. That's the problem statement, which means that T2 is equal to PV over NR, or 5 times 2.46 divided by 1 times 8.2 times 10 to the minus 2 is equal to 150K. So we're going to use this. We're going to use this expression to say delta S is equal to 1 mole times 3/2 R 8.314 natural log of 150 divided by 300 delta S is equal to minus 8.64 joule per K. And you can see why we had to go through this derivation. If you were to go back and remember our work in chapter 1, and you say, well, I'm just going to do everything in terms of heat capacity and then solve for Q, well, you're going to wind up finding an expression in which we have a 1 over T, and we have this change in temperature. So which temperature do you use? And you'll realize that set of equations doesn't work. We actually need to work fundamentally from our energy equation.